Dr. Ian Fairlie has a very broad understanding of the issues to do with low-level radiation. He's worked for many government committees, advisory bodies and regulatory agencies both here and abroad. He's also studied in quite a lot of detail the incidence of cancer around nuclear facilities and the risk that they present. Tonight we've asked him to give a talk to us for the first half of the time available, and then we'll use the second half for questions and answers. And so that's it. So please put your hands together and give a warm welcome for Dr. Ian Fairlie.
Thanks very much for inviting me to come here, and thank you for coming here on such an inclement night. Dry just about, but still inclement. I'm going to be discussing radiation risks this evening. I'm not going to talk about geology or the ins and outs of the practical issues concerned with low-level dumps. Basically, I'm going to talk a little bit about radiation risks and cover three main items, which I'll come to in a minute. In the last couple of years, there's been quite a few articles in newspapers and also in I'll just wait for a second. Quite a few articles in The Guardian and other black top newspapers, and also the BBC. All of them basically saying that there's nothing to worry about radiation and that there are very, very low risks or dangers from exposures to radiation. But a number of media pundits, including people like Monbiot, Alok Jha, Sarah Bosley, and Jim Khalili, and also professors Wade Allison and Jerry Thomas. Now, these are all British people. And they claim that the risks of radiation are exaggerated. In particular, these scientists, well, some of the scientists anyway, claim that there are no radiation effects below 100 millisieverts. To give you an idea, background radiation that we all get is about 2 or 3 millisieverts a year. And they also claim that there are no effects as a result of Chernobyl. None of that is true. So what am I going to discuss? I'm going to discuss what radiation is, basically, give you a brief introduction. Now I'm also going to talk about new kinds of radiation effects which are not taken into account by the above-mentioned people. And finally, I'm going to talk about some new studies that have just come out in the last few months, in fact, which give cause for concern, certainly calls for reflection as to what the dangers are from low amounts of radiation. Okay, radiation in a nutshell. I'll talk about these 5 things. I'm going to talk about the main sources of radiation, a little bit about how we look at the risks. I'm going to talk in particular about the dose-response relationship, in other words, the relationship between how much you get, what the risks are further down the line. Talk about background radiation and talk about a little bit about politics, which is where you guys come in. When I talk about radiation, most people think about radiation as being X-rays, and indeed medical radiation is one big source of radiation to us most of the days. But background radiation is quite important too. And all of us here, I think, were alive during the 1950s and 60s when we were all exposed to background radiation from atmospheric test bombs. And also we were all exposed to plume from Chernobyl in 1986 as the plume went across the whole of Europe, including Britain. These are some examples of exposures. The atomic bomb survivors back in 1945, the 2 bombs, Hiroshima and Nagasaki. Well, the average dose there was about 200 millisieverts. We all know about the space station which is circulating the Earth. The workers inside there you get about 170 millisieverts, and that's the main reason why they have to change. It can only go up there for about 5 months, 5.5 months, and they have to come back again. It's because of the radiation they get. Most people don't tell you that, but that's the real reason. Also, the background radiation, as I mentioned, between 2 and 4 millisieverts a year. The public limit in Europe is 1, and if you go to London, from London to New York, you get, and back, you get about 0.1 of a millisievert, and if you have a chest X-ray, you get about 0.05 of a millisievert. Radiation risks are very difficult to assess, and it's a fraud issue. There are wide differences of view about radiation risks. There are big interests involved. The military are heavily involved, the nuclear industry is involved, and the government, right up to its neck, is involved. And there are public fears about radiation. So it's a fraud issue. A lot of heat and not a lot of light. And what I'm going to try and do is give you a judicious mix of heat and light, but mostly light, I hope. These are some things about radiation risks. We can't hear or see or feel or smell. It's insentient radiation. It's inequity distributed throughout the country. Some areas get it a lot more than others. You can't really avoid it in terms of background radiation. It causes hidden changes. For example, cancers, which only occur after latency periods of 2 to 20 years or so. And it causes dread illnesses. Cancer is feared by many. Difficult to explain, and as I say, I'll just come back, different views among scientists. Radiation ticks all these boxes. So it's a funny old issue to discuss. Now, when we discuss what the risks are at low levels, as you decrease the dose down to 0, the risks go down. But the shape of the response relationship is difficult to ascertain. Some people say, oh no, it's really, really serious. It's much higher risk at low levels. Others say, in fact, it's good for you, because if it goes below the line there, it means that you're getting benefits. The ICRP, the HPA, almost all radiation authorities go for a straight line down to 0. At 0, no dose, no risk. That's the only time that there is no risk. And that's probably about the best we can do for the time being. However, this is the very latest from the Hiroshima and Nagasaki bomb survivors. Can you see behind you?
Yes.
Down, this is 100 millisieverts, 50, and then down to 0. This is the dose response. That's a linear here, the dotted line here. But in fact, it wobbles up and down a bit. Well, that's about the best we can show. The key thing here is that these figures are statistically significant, meaning that we're real, we've got big numbers here.
Sorry, can you explain what MSV means? I'm not quite sure.
Millisieverts. It's a unit which explains how much radiation you've got. Am I going too fast here, perhaps?
Yes.
I am sorry. I haven't explained what a millisievert is because I could be here all night explaining what a millisievert is. Just accept that if we're measuring the length of a table, we measure in so many meters. It's a unit. Right. And so a millisievert is a thousandth of a sievert. Sievert is the name of a bloke who died 20 years ago, who was very famous for the work he did in radiation.
Thank you.
Okay. So that's what the relationship is. The key thing to take from this is that that there's no level below which there are no effects. If you've got some level, there's always an effect, all the way down to 0. That's important, because even at tiny, tiny levels, 1 or 2 millisieverts, there's still an effect. So there's no safe dose. There's only what the authorities call an acceptably safe dose. Here are some of the limits that are placed on our exposures to radiation over the years. Back just after the war, it was 44 millisieverts a year. As you can see, that the risks, as our knowledge of radiation dangers have increased, the limits have gone down. So as we find out more, we always have to tighten up the limits. And since 1990, we're presuming that we don't need, there's nothing more to learn, so there are no more risks. Well, that's crazy. I'm going to show you that there are. And we should really be tightening up. My best guidance would be to say that a limit should be about 1/10 of the millisievert, 0.1 millisievert a year. I'm going to talk now about background radiation, to which all of us are exposed, and there's not much we can do about it really. We're all exposed to external radiation and internal radiation. External radiation, that's the prodigies and radioactive substances in the soil, which radiate us upwards. And there's constant rays from the sun and from the outer universe, extragalactic rays. And they contribute about 1/3 of their radiation to us per year. And then internal radiation is the radon and thoron that we inhale, K40, potassium-40 inside our bodies, and eating these radionuclides, the uranium and thorium series in food. And they give us about 2/3 of our background radiation. So remember that external is about 1/3, internal is about 2/3, roughly speaking. And we get this all the time without even thinking about it. And the intriguing thing about background radiation is that most people think, oh, hey, it's perfectly normal, it's natural, nothing to worry about. Well, it's dangerous, I'm afraid. The Health Protection Agency has estimated that about 5% of all cancer deaths are due to background radiation. Them, not me saying that. Richard Wakeford, who some of you may know about because you've crossed swords with him, he says that the background radiation causes about 1/5 of all child leukemias. I'll repeat that. Richard Wakeford, who is no apologist for the nuclear industry, claims, and he's written a number of articles about this, that background radiation causes about 1/5 of childhood leukemias. Could be more. And indeed, a number of scientists now think that the reason why older women have so many miscarriages and spontaneous abortions is because their fetuses get exposed to background radiation. And but more important than that, that happens during the 9 months when they're pregnant. But before that, from the time that they're born, the mothers are born, their stock of egg cells steadily accumulates background radiation for 40 years or so. And then during that time, their cells, their ova, degrade effectively. That means the chromosomes and DNA inside the woman's egg cell degrades so that when it's fertilized, it goes wrong, basically. So and that's why women who are aged over 40 are recommended not to have children, essentially. Now that's never really explained, but that's the God's honest truth about it. That's why it happens. And the final issue is that many people may think, many people that I know think that that aging is connected with radiation. It's partly why we die. It's a regular clock ticking all the time. And it degrades ourselves, basically, until finally we clock it. We've had enough. Politics and science, yeah. There's a lot of politics and radiation. I won't go them into great detail, but everywhere you look, There's a lot of political influences on how we perceive radiation and its risks. These are just some of the stuff that I've encountered over the years. The United States and the UK have put pressure on governments and scientists to reduce this is relative biological effectiveness of different kinds of radiation. And they've said, put the pressure to reduce these values. And that happens particularly with tritium. And that means, for example, the ICRP, the International Commission on Radiological Protection, refuses to recognize how dangerous tritium is. Some scientists think that radiation is actually good for you, which is almost an oxymoron. I can't get my head around that. There's a lot of denial of various studies showing that increased radiation risks. And of course, what often happens is that this is really bad. The scientists say, well, look, there's background radiation out there, it must be okay, therefore don't worry about it, therefore a little bit more will be all right. They actually say that. And that's really so dishonest. And just recently there's been a number of studies, I'll go through them in a minute. And these are in scientific peer-reviewed journals, some of them written by me, showing that radiation risks are greater than currently accepted. I'm going to be showing new evidence from, first of all, biology, which means cell cultures, and animals, and also from epidemiology, which means us, humans. We're not allowed to, well, with cells and animals, we inject radiation or radioactivity into them and we watch what happens. We do that less and less with animals. We used to do it with mice, but less and less now. We use cell cultures mostly. You're not allowed to do that with humans, although it has happened way back in the 40s and 50s. But instead what you can do is look at irregular patterns of illnesses or morbidity in an area and try and assess what the cause of that is. Okay, first of all I'm going to talk about the biology, in other words, not the human stuff, but the cells and animal studies. Essentially, maybe I should skip forward here. Yeah. How radiation scientists now describe what happens when radiation hits you is as an effect of on DNA, and it's basically single strand and double strand breaks. The double stranded of double helix of DNA molecule, and the radiation either directly or indirectly hits the strand and breaks it. And sometimes just one strand is broken and it uses the other strand as a template to fix it, or sometimes both strands are broken by radiation. Now this is this sort of theory of radiation effects has been around for a long time, at least since DNA was discovered in the mid-50s. And it explains a lot, and it fits in with the current level of radiation risks that we've got in terms of target size. But there's a problem with it, and that is it doesn't describe a whole series of new, what we call untargeted effects. In other words, by the word untargeted, what I mean is the target isn't DNA. And if you ask me what is the target, well, we don't know. All we know is that a whole series of weird effects have started showing up, which don't involve damage to the DNA. Okay? So radiation comes in, it does two things. It damages our DNA in the classical way, the classical paradigm, and it also has these other effects. Here they are: genomic instability, bystander effects, and mutations in repeated DNA. I'll show you that in a minute. This is not the DNA being hit. It's just that what happens is that the effects are that we see weird things happening to DNA, even though it's not been hit. That's what this is involved in. So we get these three effects, which are really loony. I mean, most people, for a long time, people didn't believe it because they're so strange. But now we do believe it, and there's now been what they call a paradigm shift. Hands up those who've heard of the phrase paradigm shift. Yeah, paradigm shift. It's a new way of thinking, yeah? And these are a number of, I just hauled them out of PubMed, of studies which the title of them have got paradigm or paradigm shift in them. There's about a dozen there, I suppose. Just to show you that it's not me just making this up. The other scientists are out there doing this, thinking this. So I'm going to talk about genomic instability. That's the first one. Remember, I gave you three. And the first one is genomic. What this means is that we see effects which are remote in time from the initial radiation blitz or initial lesion. For these little circles here are cells, okay? And I told you about cell studies. So when the radiation hits a cell, then normally you get effects right away, within one generation, before the cells have time to reproduce. But what's happening with genomic instability is that you have all these cell generations. You have the first generation here, second generation, third, fourth, fifth, all the way to 30th generation, sometimes 50 generations later, and then suddenly you have all these effects. I've only shown 1, 2, 3 generations here, but because I don't have a big enough board to show you, it would be from the top all the way down to the bottom. But many generations later, boom, the genome just falls apart, effectively speaking. And this is weird, man. What? And the only thing that's happened is that you gave them an initial dose of radiation. And these are all the kinds of effects you can get, as well as the gene mutation. So, so you have these effects remote in time. For example, here it says after 10 to 30 generations, it's induced. These effects are induced at very low doses. They happen very often, both in vitro and in vivo, though I've explained to you what that means. In vitro means in a cell dish, cells, petri dish, and in vivo means live animals, like mice or rats. Okay? So that's important, by the way, because you can see things in cells that you don't see in animals, because animals, including us, we've got some pretty sophisticated mechanisms for repairing damage that ordinary cells, by naked cells, don't. So you have to, whenever you're looking at risks, you always try and get in vivo, because that's a sure sign that something serious is going on. We don't know how all this works, by the way. We don't know why it works. But funny enough, bystander effects are involved. Now, bystander is another effect. Bystander effects are remote, not in time, but remote in place. In other words, they happen far away from the cell which is originally hit by the radiation. So you have a cell hit by radiation here, and you have this cell here is suddenly affected, even although it's not been hit, or this one, and this one are also damaged without being hit by the radiation. Ugh, what's going on here? And it appears that what happens is when you have radiation hitting a cell like this, is that, and you take away the radiation, is that you have little waves going around all the cells in the culture when you have these signals going out, and all the other cells respond. And it happens not just once, but all the time, up for about maybe an hour after you hit the radiation initially. So these are really strange effects. Now, and they're not taken into account, by the way, in our current dose limits or risks. So these bystanders are, again, very low doses. High frequency affects both kinds of cells, both germ cells and also body cells. Again, both in vitro and in vivo, thought to be via cytokines or reactor species. These are the kinds of effects that we see, by the way, just to know you that we have all these things happening. Now, I'm going to talk about the third kind, which is mini-satellite mutations. But to do that, I have to take one step back and tell you about DNA. This is a nice slide of DNA molecule. And for those people who remember their high school or college classes, the DNA is joined together, these gaps, by phosphate bonds and by protein bonds. And they join in a very precise way. Adenine always goes with cytosine and guanine with thymine. So it's ACGT, okay? And they don't join with others, just those two. Adenine always with cytine. That's really important because that's the chemical basis for the genetic code, basically. You may say, well, Ian, why are you going on about this? Because it's important. Remember I said the adenine forms a thymine, guanine with cytosine? You see how they always link up with each other? Right? Now, what this is here is the length of the DNA which comes from a chromosome. This is a chromosome here. For a bit of the chromosome, we'll get this. Now, this is actually what you actually see if you unravel the DNA. You see these joints. It's called tandemly repeated DNA. You'll see this bit here, AGGDT, here, AGGTT, is repeated. Look at it. Yeah. For hundreds or thousands of times. Whoa! Now, this is non-coding for protein areas of the DNA. In other words, it doesn't make proteins. And for a long time we thought it was junk DNA. Hands up people who have heard the phrase junk DNA. Yeah? That's what they thought junk DNA, but now they know. Did you think that the mammalian genome would faithfully reproduce this for millions of years for nothing? No, nature doesn't do that. And this junk DNA has a very serious set of purposes. It's called epigenesis. The trouble with this repeated DNA, if you affect it with radiation, it causes big time effects. These mutations are called mini and micro satellites. They affect non-coding DNA. They're not junk. We know them to be functional, these long sequences. If you muck around with them, and change them, mutate them, there's lots of diseases affected with that. They're very sensitive to radiation, hypermutable. And we don't know how they're caused. Just like bystander, just like genomic instability, we don't know why these things happen. In other words, it's not by hitting the DNA. But it results in these changes in the DNA, but not the double strand breaks or the single strand breaks. We think it's mostly through males. So men, it's all our fault. And radiation is strongly implicated in the changes. So these are all the untargeted effects, all of them, all three of them I mentioned, and there's others. We think that it's got to do with inflammatory responses. We think that all these changes have to do with inflammation. In other words, it's a natural thing. And we think there's some genetic factors involved as well. Anyway, what happens is that when you go, these mediate the response, and you have cell survival, and but a damaged cell surviving, and you have increased risk. But also you have genetic factors where you have cell death. Contrary to what you may think, cell death is a good thing because it kills the mutated cell. And cancers cannot result from a dead cell. Okay? Impulses. And you have decreased risk. But we think that there's more this way than this way. So with these untargeted effects, by the way, some people say non-targeted effects, same thing. Well, with them, are we underestimating risks of radiation at low doses? The problem is that right now we get our risks from the classic effects. But these new effects occur at much lower doses. And the new effects are in addition to the classic effects because there's really good evidence for DNA being disrupted double-strand breaks. We can actually see that under microscopes. What about transgeneration? In other words, effects further on down the generation. Anyway, this is a more detailed one, basically saying that we shouldn't really apply drafts to our radiation risks. By that I mean, right now we deliberately reduce the risks because of low doses, and we shouldn't really do it. It's called the dose and dose rate effectiveness factor. So, I'll just skip that one. What are the implications for risks? Well, the Cherry Committee, which is, this stands for Committee Examining the Radiation Risks of Eternal Emitters. And for better or worse, I was the scientific secretary on that committee for 4 or 5 years. And it was divided on this because it looked at these in quite a lot of detail. The official scientists said, no, nothing to worry about, but all the other scientists who were from Friends of the Earth and from Greenpeace said, whoa, yes, there is. Authoritative, quite a few good scientists, and I've mentioned the names here, state that the perceived risks have increased. But the officials say, nah, nothing to worry about. Well, the problem is that they know that there's something out there and they don't take a precautionary attitude towards it. Okay, so all of that is about cells. Now I'm going to talk, do you want a break? Yeah. Shall I go on? Talk about humans? Yeah. And I'm going to talk about 4 things here. First of all, about background radiation, medical exposures, people living near nuclear power stations, and the Chernobyl cleanup workers. Now, the thing about these are all low doses. Right? These are tiny doses. Background radiation, what? 2 or 3 millisieverts a year. That's very small. And most people think that the exposures you get from X-rays are small. Yes, in most cases they are. People living near nuclear power stations, do they get any radiation? Well, according to the authorities, very, very little indeed. And what about the Chernobyl cleanup workers? Now, those are 4 areas, and I'm going to show some studies in those 4 areas which reveal a much bigger risk than we thought. Okay? These are all new-ish. First of all, background radiation. Well, as I mentioned to you before, Wakeford and his colleagues have they used a couple of risk models and various estimates of the bone marrow doses received by children from background radiation. And they found that about 20% of the cases in the UK were attributable to background radiation. Why red bone marrow? Well, many of you may know that leukemia is a disorder, cancer of blood cells, white blood cells in particular. But both white blood cells and red blood cells are made in our bone marrow, inside the middle of our bones. And there's a good reason why it's made there, the cells are made there. It's because that's the one area which is protected most from background radiation. When you have an X-ray, the bones show up because the bones block the actual X-rays. And so what you watch in the film, the X-ray film, is a shadow. Bones are very good about blocking X-rays. And so in the middle of the bone is a good area to protect these very fragile and very radiosensitive cells from being hit by radiation. But some radiation gets through. And what happens is that the white blood cells, leukocytes, are damaged by the radiation. And when they're made, when they reproduce, they form big cells which don't carry out their function. And they effectively block out the good cells. And the kid loses their immunity and they die from opportunistic infections. That's leukemia in simple language. So you've got to look at the doses to the red bone marrow. And that's what Richard Wakeford and his colleagues did. Some of you may be thinking, hang on, who is this guy Ian Fairlie? Is he a friend of Richard Wakeford? Richard Wakeford's no friend of ours. Interesting. Wakeford worked for the nuclear industry for a long time, and he was on Cherry, the committee that I mentioned before. And we go back a long way, and we're, although we look at, certainly we have different views about the nuclear industry, we have respect for each other. And his work is generally quite good. In fact, I'd say his work is very good. But some of his views, well, we differ. I think he probably has exactly the same opinion of me, 180 degrees around. So this is background radiation 1. Okay, let's go to background radiation 2. Very recently, last month in fact, two scientists, a US guy and a French guy, studied radiation effects in areas with high natural background radiation. In other words, monazite sands where there's a lot of thorium in the sand. And they found increased risks in these things, immunology, physiology, mutation, and disease. And the author stated, and I'm going to read it to you because this is new to me as well, he said, if we see effects at these low levels, and this is background radiation, just slightly raised, then we have to be thinking differently about how we develop regulations for intentional exposures to populations, like the emissions from nuclear power stations, medical procedures, and even some X-ray machines at airports. Oof. He said that, not me. They said it, not me. Interesting. And I agree with it, but it gives you an idea of what's happening is that we're changing our views about radiation risks here. Okay, number 3. This was a Canadian study in 2012, which they looked at lung cancer deaths in Canada and radon concentrations, indoor radon concentrations. And they said that their calculations showed that about 16% of lung cancer deaths in Canada were attributable to indoor radiation exposure. And this is the Canadian government saying this. Interesting. And now I'm going to go on to medical exposures. This is a study, again, this year, June the 7th this year, which published in The Lancet, which showed that CT scans, computed tomography scans, cause significantly increased risks in children under 3 years old. It's really worrisome. And now I know that the advice is going out to doctors, don't expose kiddies to CT scans unnecessarily. You have to have a really good reason for doing it. They found that 3 head scans to a kiddie under 5 tripled their risk of having brain cancer. Woof. And between 5 and 10 scans tripled their risk of leukemia. Oh, God, it's terrible. It really is. Do we need to do this stuff? Well, I mean, the balance is fine in many cases. By the way, this doesn't apply to adults. This is children I'm talking about, okay? Adults seem to be more radio resistant. It's children that's a difficulty. Maybe I wonder if I've got a picture of it. Yeah, here's a CT scanner here in hospital. How many people have ever seen or been had a CT scan? Oh, right. Okay. The average, depending on what you get and how many times you have to go back and all the rest of it, but one scan from between here and here, it gives average about 25 millisieverts. Okay, and it was 8 years worth of eight background years worth of radiation. Okay, one scan. What happens, of course, is that you have an X-ray slice done of you, and then it's multiplied because it goes round. The machine goes round you. You're lying like this, and right round you are the thing stops and rotates, and puts slices through you like this of an X-ray. Slice, 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 360 degrees, and a computer program, well, a number of programs, add them all up and give you a three-dimensional image on the TV screen. It's great. I mean, the actual images are just amazing. Doctors think they're wonderful. And in my case, they picked up a cancer because recently I've been in hospital for cancer. And so I am not going to say nay about them, but there are big doses for kiddies. Yeah. And now in Britain, the National Health Service has said they will not allow scans, phishing scans. In other words, while you're healthy, we'll just take a scan to make sure that you're okay. Insurance companies do that. They say, well, you want insurance, right? You have to have a scan. And they'll find things which you have no symptoms of. And the NHS says, well, Rev, you go ahead and do it, but you're not getting treatment here. And that's absolutely right. Because if you've got no symptoms, then fine. As soon as you get a symptom, then, of course, go for the scan. But oftentimes you can have asymptomatic things which you shouldn't get any treatment for. I'm not talking about cancer, I'm talking about many other things. So it's a big issue, health policy-wise. Okay, second on medical exposures. Now these are small doses again. This is for cardiac imaging. It was heart. And these scientists found in 2011 in Canada again, for every 10 millisieverts from cardiac imaging, there was a 3% increased risk of cancer. Well, you can easily get 100 millisieverts from cardiac imaging, depending on the procedure that you use. So you could have a 30% increase in cancer risk. These are eye-watering figures. The thing is that, of course, you're often dealing with cancer here, and you want to deal with these things, or because if you don't have the cardiac imaging, or if you're talking about heart disease, you might die. And so you take the image to try and preserve your life or prolong your life. But the risk is that later on in life you're going to die from cancer, or you have an increase. So it's a Faustian pact in a way. The really eye-watering statistic is that in the United States, 40% of all people who die from cancer are secondary cancers from their treatment for the first cancers. It's incredible. It's a real epidemic in the United States. And in Canada, they've blocked the use of asymptomatic CT scans. And they've put on very strong recommendations to doctors to be extremely careful about their use of CT imaging. And this is what these doctors said. These results call into question whether our current enthusiasm for imaging and therapy procedures after acute myocardial infarction should be tempered. That's them saying it. Okay, nuclear power stations. Most people don't think that there's any problem with nuclear power stations, and certainly in Britain, the government goes out of its way to play down any dangers on that. But there are problems. In particular, there's a big study in 2008 in Germany, commissioned by the German government, which found big increases in childhood leukemias and embryonal cancers near all German power stations. An embryonal cancer means that when the baby is born, the baby has got solid cancers already. This led to studies in France, UK, Switzerland, Germany, and another study in Germany, which all found similar results. And these are the studies here: Germany, Great Britain, France, Switzerland. And if you pool them together, as we've done, you get a statistically significant result. Just accept that if the p-value here is greater than 0.05, then you really have to take it on board. And if you pull them together, you get very significant figures. These show, that's a standardized incidence ratio, which is just the observed divided by the expected. Right? For say you got in Britain, you observed 20, but you only expected 15. The reason why it's 15.4 is you're looking at population data, and so you wind up with part numbers. Divide this into this, and you get 1.3, which means a 30% increase in leukemia cases. And so altogether, there's a, roughly speaking, 40% increase in leukemias, in childhood leukemias, within 5 clicks of nuclear power stations throughout Europe. Well, if you were, my view, if you were an honest, sentient human being, that means you look elsewhere for your energy policy, basically. We shouldn't really be producing nuclear power stations, or promoting nuclear power stations which have these figures. I don't know what your views are about energy policy, but anyway, that's my view. And the fourth, remember I told you those 4 things: medical background, nuclear power station, and Chernobyl. This has just come out in November. Oh, by the way, the reason why I've got these data here on this, because anybody who wants the slides can have them, and they have all the data in them, all published reports, and the references, so you can do your own studies and make sure that I'm not selling you a pup or anything like that. But this is the cleanup workers, and they had big doses. Some of them had 400 millisieverts, that's 0.4 sievert. Some of them 200, some of them had 100, 50, but you can see quite a few of them had very small doses. And when they did the analysis, they found a very straight line. You remember I was talking about what the relationship was, whether I wobbled up and down or not, and that's pretty good evidence of a linear dose-response relationship. And here's a whole pile of other references, just in case you didn't have enough. And here's some nice articles to read if you're really, really, really interested. And I'd like to thank some of my colleagues. Okay, thank you.